finish up some of the last things in Chapter 15. You've got those textbook problems posted up there, which I think are all on Canvas now as well, okay, for both 15 and 16. So the thing that we ended with on Thursday was looking over the idea of a acid dissociation constant, otherwise known as an equilibrium expression with respect to an acid. And that's just a frame of reference, just something to look at and add some information to our problem solving. Okay? And the reason it came about is that if we take a look at these two equations, they're very, very related. We're looking at ultimately the same acid being involved in both these equations. We've got an acid here, and we've got that same species over here. Okay, so these equations are intricately related. They're ultimately the reverse of one another. Okay, so what we want to do is look at equilibrium expressions for each of these. Okay, and just because we have similar terms doesn't mean the equilibrium expression is the same. If we went through and solved for the equation 1, what would our equilibrium expression look like? K equals our products. So we have H3O plus. I wrote this way too large. Over H2, H3O2. Why do we not include water? Because it's a liquid. It's in a different phase. We don't need to worry about it. All right, if we went through and did K2, would we get the exact same thing? All right, let's go through and take a look at what K2 would generate. Because I gave myself so much space. K2, what are our products? Times the concentration of, we could go through and write the lithium hydroxide, add the lithium in there if we wanted to. That's the same as writing OH minus. Why is it the same? It completely dissolves because group 1, we're looking at a strong metal that completely dissociates. So lithium hydroxide is the same as writing hydroxide. This would all be divided by, and here I'll pull the lithium out. Is K2 and K1 the same things, or are they the same things? Can you tell a difference between them? I believe one is orange and one is red. Can you tell a difference between them? Okay, good, yes. We see orange versus red. Are the equations the same? Do we have the same things showing up in the equation? No. Okay, so they generate different equilibrium expressions even though these equations are very related. Okay, so what someone went through and did is said, okay, I need to put a frame of reference on this. What's my reactant? What's my product? Okay? Or we could look at the solution generated. When we add HC2H3, I did that right, HC2H3O2 or acetic acid to water, we generate H+, which means the solution becomes acidic. What happens when we add the lithium acetate ion to water? We generate base. So that solution is basic. So instead of referring to these as equilibrium expressions with respect to acetate or equilibrium expression with respect to acetic acid, because that can be a bit of a mouthful, we'll refer to the overall solution. Is it acidic? Is it basic? Okay? So when we go through in that first one, we said it was acidic. We go through and look at the next one, say it's basic. So instead of referring to them as those larger K expressions, this is where we come in and call them Ka and Kb. Okay? So when we're generating an acidic solution, if we see H3O plus on the reactant or product side, we have an acidic solution. If we see OH minus show up on the product side, we have basic solution. So it's a question of looking at those different equations, looking at what you generate, and defining those equilibrium constants appropriately. Okay? The next part of this that is helpful is if we go back through and start to add these equations up. Okay? So what we want to do is now go through and compare each side of the equation. What terms can cancel out? So we said the equilibrium constant for our first one was Ka.
I'm sorry, again, how do we determine if that was acidic and it was basic?
You look at the product side and look for either H plus or hydronium, H3O plus, or you look to the product side and you see OH minus. Okay? So we've got Ka for the first one. The other one was Kb. If we now go through and add these two equations up, we see things that can start to cancel. Does our acetic acid show up on both sides of the equation? Yes. So we can cancel that. Lithium ion shows up on both sides. We'll go ahead and cancel that. How about the acetate ion? Okay. We can then go through and add these two equations together, and what we get okay, why is this interesting? What's the K expression for this? It's the Kw. Okay. Why is this further important? What happens when we add two equations? What happens to the equilibrium constants? If I wanted to solve for Kw, Kw is equal to H3O plus OH minus, but it's also equal to Ka times Kb. This becomes important because if we're going to go through and try and solve problems or come up with tables of equilibrium constants, we only have to determine one, either the Ka or the Kb. Why do we only need one? Because the other one we can solve for, okay, using this expression. When can we solve for it, though? That one's a little bit. When you know the Kw, when is the Kw 10 to the minus 14? It is at equilibrium, and I think someone else said it. It has to be at 25 degrees Celsius. Okay. As soon as we change the temperature, that equilibrium constant also changes. We have to be aware of that. As far as the problems that you're going to end up solving, we're assuming room temperature for all of them unless otherwise stated. Okay? So if you go through and look at a problem and they give you the Ka, but when you draw out the balanced equation, it's for a basic solution. Does that Ka apply? No. We'd have to convert to the Kb to make sure that we're looking at the correct equation equilibrium constant relationship. Okay? So be aware of that when you go through and try and solve problems. Okay? The question 4, I think, on the quiz has you go through and do this relationship. Or you'll need to use this relationship. Okay? Now we're going to kind of skim through some things that I kind of just want to mention. Are all compounds acids and bases? Okay, we end up with 2 answers to this. The easy answer, I don't actually remember what I said. We went through and looked at these 2 reactions. Can't really define these as acids or bases, okay, because we don't see any hydrogen ions or hydroxide ions show up in the product side. Okay? So we could go through and say no. However, there's a harder answer to this. That harder answer is yes. Absolutely. Everything acts as an acid and a base. So one of the things that's interesting when you get to organic chemistry. But we have to change our definition a little bit. Okay? When we look at Bronsted-Lowry acids and bases, it's only with the transfer of a hydrogen ion. Not all reactions involve just the transfer of a hydrogen ion. Ultimately, what's changing when we go through any kind of reaction? Okay, so if we picked a standard acid-base reaction, add that to water, what do we get? Close. H3O plus and Cl minus. So this is how we would typically write it out. There's a slightly better way to do that. Instead of drawing H3O plus, we could draw H2O with an extra line saying a bond. What changed as we went across this reaction? Go back with your standard definitions. Go easy first. What changed? The electron count didn't actually change. The location of the hydrogen ion changed, right? We took that hydrogen ion that was originally associated with chloride and we now put it on oxygen. So we could look at the change of the atom position. Okay? Interesting thing about atom positions, though, they're going to move all the time. We aren't so much concerned about where that atom is located as the electrons that are associated with it. Okay? Why is, in the reactant side, the hydrogen next to the chlorine? Is there anything holding that hydrogen next to the chlorine? 2 electrons in the bond. So really, when we look at our definitions, we can expand this, and instead of looking at atom motions, which, remember, all atoms are going to move constantly. Okay, you could look at human interactions as well. It's the same kind of thing. If you end up getting couples, they're forming a bond. We all move around. We all interact with everybody else. That doesn't mean we become a couple. Okay? Or larger groups of couples, if you will. Okay? What really happens is we have to have that special interaction that allows for a couple to be generated. That's that energy in between them. If we wanted to, we could call that love. In the case of chemistry, we're looking at the electrons. So what we can do is change our definition. And instead of looking at atom positions, which ultimately are going to move regardless, we can look at the location of the electrons. And so we expand our definition into what's known as the Lewis definitions. You're looking at Lewis acids being electron acceptors. Can that atom accept electrons? If we compare this back to an acid, okay, what happened when we took HCl and we added it to water? And we moved to our H3O plus and Cl minus. What did that hydrogen ion do in the course of that reaction? Okay, we know it's an acid. It's H plus. Okay, so to stabilize it, what does it need? Electrons. Where are their electrons? On the oxygen. The oxygen can share electrons with that hydrogen. That hydrogen has now become an electron acceptor. Okay, so what we have is now a Lewis acid. It's just a change in the spin of how we're looking at that overall reaction. Do we look at the atom motions or do we look at the electron motions? When we move to the base, water had to act in the base in this case because it accepted the hydrogen ion as it shifted over to the product side. Okay? What did it do to accept that hydrogen ion? It had to share electrons with the hydrogen atom. So what we look at as a Lewis base, an electron donor. These definitions, and your Lewis definitions in particular, become critically important when you move into organic chemistry. Okay, so you'll see a couple examples show up both in your homework and on the exam as far as applying these definitions. Okay? They are insanely important. You will 100% get tested on them. Okay? So please read up on that chapter, get kind of comfortable with what's happening within it. Those are going to be questions that will require you to not show your work because ultimately all you're doing is looking at how the structure changed. Okay? So just kind of be aware of that. Questions about your Lewis definitions? Yes?
I'm just confused because isn't the Bronson acid, isn't that an electron donor?
What's the definition of a Bronsted acid?
Acid. Only proton donor.
Proton donor.
Yeah.
So what are we saying an acid is in the Lewis definition? An electron acceptor. What does a proton need to do to become stabilized? What charge is the proton? Positive charge. What does it need to do to become stable? Accept electrons. There's your definition. Okay. They're all intricately related. You're just looking at them from slightly different vantage points, which makes it a little bit trickier to deal with. Why is the Lewis definition so much more difficult than anything else? We're looking at moving electrons. How do we show electrons typically when we're looking in general chemistry? We could do it in the Lewis dot structure. How often have you seen me draw lone pairs on all of the structures that we've looked at? That didn't really show up. Okay, so maybe there was another way. We could show it with bonds, right? That line in between atoms representing that. If we take a look down at the very last example, CO2, how many lines do you see there? None. One of the big issues that I have in particular with general chemistry is that we've removed all structural interpretation, which means you are left solely with, this is a formula, memorize the mathematics behind it. Okay? You don't get a grasp of the understanding on what's actually occurring or changing as these structures transition. You get that a lot more in organic chemistry. Okay? So what you need to be responsible for is how you manipulate the mathematics. Realize you'll see these kind of problems show up. There's no mathematics to them, so yippee, right? You don't have to worry about calculator mistakes. You just have to be very careful about how you apply those definitions. Okay? Other questions with Lewis acids? Okay. Next thing, the chapter or your book goes into a very large section on amphoteric compounds. As you can tell, I have a very high opinion of amphoteric compounds. Ultimately, it just means that the substance can act as an acid or a base, okay, depending on the conditions that you give it. They then go through and describe a whole bunch of different oxides and describe how they would act in certain reactions. So if it's a metal oxide, it acts as a base. Most non-metal oxides act as acids. Okay, those are your general trends. What happens as we move across the periodic table? We move from metals to nonmetals. So what happens right in between when we transition between a metal to a nonmetal? Now all that chemistry goes out the window. We lose kind of our trends. And what we're looking at is that in-between space where something transitions. In that transition, we could refer to them as metalloids. We're going to see different chemistry as well. So in that kind of metalloid transition, we end up with amphoteric compounds. They could act as acids or bases, depending on the conditions given. Okay? Anybody interested in amphoteric compounds? Jerk. I'm allowed to say that about it. Okay. Not that big of a deal. Read through the chapter, get an understanding of it. The only way you'd get tested on it is I would directly tell you something about a compound being amphoteric. Okay? I do not expect you to memorize what compounds are amphoteric or not. Okay? Given an equation or a sequence of equations, you should be able to decide if it is amphoteric or not. Okay? So how would you decide that? Drop the compound into water. What would you expect to see? Both acid produced and base produced, okay, as possible interactions. We'd have to draw that in two separate equations. Okay? So not a huge issue to be concerned about, but it does show up in the textbook. I'm not even sure how I can write a question directly about that. Okay? So that section is very, very weak as far as exam material. Okay? The next part that's actually going to become really important is what the textbook, I believe, refers to as salt effects, or the acid-base characteristics of salts. Change that title around a little bit because we're going to end up seeing it show up in chapter 16 as well. Okay, I think they start chapter 16 with the same idea. Okay? So what we're going to do is look at the effects of particular ions on an individual solution, because that can be important to the overall acidity or basicity of it. Okay? So what we want to do is take a look at what happens to the pH if I add some of the conjugate base to some of the following solutions. Why look at the conjugate base? What charge is a base? Negative. What's another name for a negative species? Anion effects. Okay? So that's what we're looking at. We're going to look at the conjugate base. There's our anion. So what happens when we add the anion to the solution? Okay, so if I just take chloride ion and add it straight to water, does the pH change? Does the chloride ion react with water? What would it produce if it reacted with water? So what we want to do is say, okay, let's take chloride, add it to water. What do we get? We're going to pretend that reaction works. HCl and OH minus. So our initial assessment would be what happens to the pH? Goes up. We're becoming more basic. Okay. Now what we have to do is evaluate that reaction a little bit more carefully. Okay. In the process of doing that, I make what species? Not only is it an acid, but it is a strong acid, which means it completely ionizes as soon as it hits water. So if we go back to that reaction arrow that we had initially put in there, which way does this reaction go? Left or right? It only goes towards the left. Because if we go to the right, we generate a strong acid that immediately goes back towards the ions. So what happens to the pH if we add chloride ion? Absolutely nothing. Chloride ion sits in the water, does not react with the water, it does not generate hydroxide, nothing changes to the pH. Okay? So the conjugate base of a strong acid does absolutely nothing when we look at the pH. What happens if we change our acid? Okay, let's take this acid, acetic acid, okay, drawn in a slightly different format than we've seen before. Okay? It's not a strong acid. So what happens if I take acetate ion now and I add that into solution or into water? What's the product? Careful. We add an H to our acetate ion. I'm going to put it out in front so that we know it's there. Plus still back to the same question. Plus what? OH minus. Our initial assessment would be what? pH goes up or down? Goes up because we see hydroxide ion. Okay? Before we can say that the pH does indeed go up, we need to make sure that we haven't generated a strong acid. Is this one of the strong acids you've been required to memorize? No, which means what arrow should go in between? What arrow should I show between those two reactions? Okay? Right arrow is not completely wrong. We do generate some of that species, but since it is a weak acid, what does it also do? It does also dissociate. What we've got is an equilibrium arrow. Okay? So acetate ion, when added to pure water, increases the pH, makes it more basic because it can react with water in an equilibrium fashion to generate that hydroxide ion. Okay? So I'm not sure what all of that's saying. Our H plus must decrease, which means our pH increases. So yet another way to look at this. So what I went through and did, because this is two perspectives, let me go back here a little bit. Okay. If we looked at this as an overall equilibrium, okay, if I add acetate ion to this, what happens? If I'm at equilibrium and I add acetate, what in effect am I doing? Increasing the concentration of the, if I add the acetate ion, increase the concentration of the products. Which way does the equilibrium shift? Towards the reactants. Which means what happens to the concentration of H plus? Decreases, which means what happens to the pH? Increases. Okay? That whole pH system tends to mess with people's heads. Okay? So we can look at this based on just the acetate being added purely to water, or we could draw out the acetic acid dissolving in water and just saying what happens. Okay? So we can evaluate different perspectives on that same overall reaction. Okay? Yes?
What did you say? You said the pH decreases?
So the pH increases.
Okay, that makes sense.
If H plus decreases, the pH increases. They're inversely related. Okay? Questions about that? What happens if we look at a cation now? So the anion was looking at the conjugate base of an acid. Where do you think the cation effect is coming from? The conjugate acid of a base. Okay, so we could look at some of the following reactions. Our conjugate acid, not super obvious in the case of sodium hydroxide, but we're looking at sodium ion. Okay, it's the positive species. What happens when we add sodium ion to water? We could draw out that water interaction. We take Na plus H2O. What happens? We get, this is a weird one. We end up generating our strong base. What happens when we generate our strong base? Completely dissociates. What arrow should I show in between? That arrow should be aiming solely to the left. Okay? So adding sodium ion to water, we could predict what would happen to the pH. What happens to the concentration of H plus when we add sodium ion? We could expect it to increase. H plus is a product. Okay? But then we evaluate our other species. What can you tell me about this species? It's a strong base, which means it completely dissociates and it goes back this direction. Do we ever see a change of H plus or OH minus? No. What happens to the pH? Stays the same. Nothing affects it. We end up looking the exact same as what we started with. No change in the H plus or OH minus concentration. Okay? And that's all dependent on that arrow in between. Which way does our reaction go? If we generate a strong acid or base on our product side, the reaction never occurs. We never see a change in the pH. Okay? Questions on the strong part? What? Yes?
Strong bases, I know it's the group 1, and then group 2, is it all of them, or is it just the heavy ones? Group 2?
I'm not positive on the group 2s. I think a few of them are insoluble technically. Treat them all as strong bases unless otherwise stated. All right. What happens? Sorry. Yes.
So if it's going backwards towards the reactants, it's gonna no effect on pH.
Yeah.
Either with that or
So what we did was add sodium ion to water. What happens? If what we're going to do is assume a reaction occurs first. To stabilize Na plus, we need OH minus, or we need a negative, so we'll take OH minus away, we generate H plus. Our initial assessment says H plus concentration goes up, which means our pH changes. Before we can make that official, we must evaluate the other species generated. What can you tell me about that species in this case? It's a strong base, which means it completely dissociates into its ions, and effectively it can't be formed. We go backwards. When we take a look, sodium ion in water, do we see H plus or OH minus? No. No effect on the pH. So all of our predictive work ended up being useless, sort of. Okay? What happens when we move to a weak base? So now what we want to do is take a look at the conjugate acid of our weak base. Our conjugate acid ends up being, what's the conjugate acid in this next equation? Must be an acid, which means it needs to have hydrogens, and it should be positive or not negative. If it's negative, what's it going to act as? A base. Okay? So when we go through and take a look at this, our conjugate acid is our ammonium ion, NH4+. Add that to water. We said it's going to act as an acid, which means it will dissociate into hydrogen ion, which can react with our water to generate H3O+ and NH3. Our initial assessment. What happens to the concentration of hydrogen ion? It goes up. I'm forming hydrogen ion as a product, or hydronium. What happens to the pH if the hydrogen ion goes up? pH goes down. We're becoming more acidic. Okay? Before we can make that official, we must evaluate our other species. What can you tell me about that species? Fair enough. It is aqueous. Is it a strong acid or base? No, which means we are looking at an equilibrium reaction, which means the arrow I would show in between would be that both directional arrow, which means what happens to the pH? pH goes down because the concentration of H+ goes up. Yes?
Sorry, how did you know when is that equilibrium?
So an equilibrium is determined based on what we've got boxed in purple here. Okay? If this species is strong anything, by definition, it goes back towards the reactants. If it's not strong, then we're looking at an equilibrium reaction. Sorry, I shouldn't write it as if it is strong. If strong, then it goes towards the reactants. Otherwise, it's equilibrium. Okay? Questions on the ions? Okay. So that just stepwise is everything we just talked about. The next part of this is actually going to be where we'll start the quiz. So this should give you kind of access, set you up with almost everything that's covered in the quiz. If you've got questions with it, feel free to talk to people around you, raise your hand, ask questions, all that kind of fun stuff. This question shows up on the back.